Hello and welcome to another episode of Fractional Excitations, a podcast from the Tafti Lab at Boston College. My name is Fazel Tafti. I welcome you to a journey with two students, one graduate, Sudhaman Balguri, and one undergraduate, Mira Mahendru, who worked on one of the latest results from our lab. The purpose of this podcast is to mostly talk about the human aspects of research in a physics lab. And therefore, we will spend more time talking about the experience that our graduate and undergraduate students had throughout a research project. The work we're going to talk about focused on europium 5 indium 2 arsenic 6. It's a new semi-metallic material that exhibits colossal magnetoresistance. In fact, it exhibits two types of colossal magnetoresistance. The result of this research is currently published at Physical Review B as an editor's suggestion, which is an honorary position for a publication where when a paper is very good, it is usually published as an editor's suggestion.
Yeah, it was so much fun. I think that our collaboration is very unique and it's not very traditional to be working so closely together on like every part of our project, and it worked so well that like we still work on new projects together. And yeah, I think just the timing was so perfect, and like both of our skill sets that we could bring to the table were just very different, but like at the same time meshed really perfectly for what we needed in the project.
Excellent. So let's talk about those skill sets. This project really was founded on discovering how to grow crystals of this particular material, europium 5, indium 2, arsenic 6. Mira, tell us the process of finding the way to grow crystals of this material for the first time.
Yeah, so when I first joined the lab as a freshman, my first task was to grow crystals in a similar family that already existed, just helping produce crystals that we needed for collaborators. But that introduced me to this process of flux growth.
And so it means that the work done by our students was very good and it was rewarded by this recognition. This episode of our podcast is somewhat special because at the heart and center of this work was a collaboration between the two students, between the graduate student and an undergraduate student. Therefore, I would like to begin on that note. Tell us, Sudaman, about the collaborative aspect of research and the experience you had with Mira.
Hello everyone. It was like actually really a fun project. We were learning so many things, both me and Mira. And initially, when I started this project, I was doing, I was like learning the techniques of doing the experiment, like basically to extract data. And then Mira was working more on the crystal growth side of things. So it was like a nice point of contact for us after like maybe 6 months, like one semester. I was good with the getting data from the measurements, and she has already perfected the growth of this material that we'll be talking about today. So yeah, so it actually started from there, and it's been like 4 years from now, and it went great. We learned like so many things in the collaboration.
And so I had some idea of what sort of flux I should use when growing a material, what sort of heating curves I could work with, and I was familiar with the elements that we were going to be working with, and I really enjoyed it. So we started exploring similar materials to see if we could grow any in our lab and expand that area of research. And we started looking at the 526 family, and this was one of the materials that we chose to try to grow. And it took a lot of trial and error because we had to go through a lot of different heating curves and a lot of different flux options. And we ended up settling on a very non traditional flux. So it took us a long time to get there because nothing else was working. When we were able to grow it, we then had to refine our synthesis and perfect it. But I would say it was more fun than frustrating.
Indeed. Thank you, Mira. Now, to Sudaman, the other technical aspect of this research was to perform electrical transport measurements. This material exhibits a phenomenon known as colossal magnetoresistance. Maybe you can explain to our audience what is colossal magnetoresistance and tell them about what it takes to measure this property and prepare samples for it.
So just before I go into the colossal magnetoresistance, I just want to tell something about Mira actually. So when she was growing material, in the process we make tubes and we seal the tubes. Put the material in the tube and we seal the tubes. And the tip of the tube which we seal is kind of very important because it's in the process of growth. At the end, we have to centrifuge it. So the tip's quality is very important in determining if the sample will grow or not. And I think Mira makes like the nicest tips in in our safety lab actually. In like taking also the grad students into account, that's like the best tips we can see. I think that's like the one important thing that I learned. It might sound silly, but it's one of the most important thing like I learned from Mira actually.
But it's still my least favorite activity in the entire lab. That's the one thing I don't enjoy doing. But it was challenging to me, and so that part was nice.
And this is absolutely true. In fact, thanks for reminding all of us about this, Sudaman. In our lab, we have to seal the materials inside an evacuated quartz tube, and that's the tube that they're talking about. And so you need to use a high temperature methane torch to seal that tube. And it's sort of a scary thing because it's a 1000 degrees Celsius hot torch, and it's very scary to work with it. And it's true that Mira, despite this being her least favorite part of the work in the lab, it's absolutely true that she does make the nicest sealing on the tubes. And we have all talked about it every now and then in the lab. I still don't know exactly what's the magic.
Yeah, I heard like a quote somewhere which says that perfection is not like an accident, it's like an deliberate choice of thousands of many tries. I think it was like a nice learning for me from Mira. And coming to the project, actually, the main part of it is colossal magnetoresistance, which is so we basically measure the resistivity of a sample and we see how it's behaving under the application of a magnetic field. So that's why the name magnetoresistance. And in some materials, we have a very huge separation, huge change in resistance. So it's called colossal magnetoresistance. So that's basically the idea of the project to understand this phenomena. Like it's not so understood in comparison to its analogous phenomena like positive magnetoresistance, where you see an increase in resistivity when you apply field. So that's basically was the idea. And one fact that we know is there were many European based materials which show these effects, so we want to know what's so particular about it. So yeah, that's how the project started actually.
Excellent. Okay, so now going back to the material. So you mentioned, Sudaman, that this is a European based compound. And I can say that as far as your research is involved, europium is gold because it sort of endows these interesting magnetic and transport properties to all these materials. But then this material also has arsenic in it, europium 5, indium 2, arsenic 6. And we all know that arsenic is poisonous. So maybe, Mira, you want to start talking about the challenges of working with arsenic and the things you learned about doing it safely.
Yeah, so this project definitely challenged my knowledge of chemistry and, my lab skills. At first, I was pretty daunted. It was pretty daunting because I was the youngest in the lab, and that was like the first thing I had to do was learn how to deal with toxic chemicals, and there was not that many people at the time working with them. Honestly, I learned that the best thing you can do is just be calm and like approach it as calmly as possible and just be very aware and careful, and report, mentally anything that we think could go wrong or that is going wrong. Because definitely at certain points, like we found different issues working with it. So Dalman can talk more about that.
Yeah,
Awesome.
one more issue that we have is how insulating the samples are. So doing actually the measurement is could be very difficult, like doing the transport measurement, because contacts might not stick well to the sample because the sample itself is insulating. So we have to deal with very high resistances. So and I have to like try a lot of different techniques with fuzzle to see which of these techniques works better. And we ended up understanding that it's really the simplest technique, making contacts with silver paint, that was working the best. And yeah, it did take so many tries because of the insulating nature of the material.
Regarding this development of skills, let's talk a bit about that. So this was for both of you. This was your first serious project and first published paper. But of course, it didn't happen overnight. You spent a lot of time honing your skills. Sudaman, in your case, it was you spent a lot of time just knowing how to prepare the sample or polish the sample to the right size for the measurement, and then placing electrical contacts on the sample to measure transport. Could you explain how what it took to hone your skills and perfect this procedure?
Yeah, I think every grad student, when they start, they are pretty enthusiastic to work in the lab. Like I am right now too, but I want to do more of data analysis as well at this stage. But initially, people will be very interested to spend more time in the lab. We are also very young, so we can like spend many hours in the lab. So yeah, so that's like a good time to learn like a new skill. Before coming to Tafty Lab, I don't have any experimental actually an experience. So yeah, it was pretty difficult in the beginning, but it was also fun to spend those hours.
Coming into the lab, I had no idea how to do anything really in a lab space. I thought I wanted to become a chemist, I think, at first. And so I was particularly interested in like this lab and growing materials. And then it got to the point where we successfully synthesized the material and I had to do magnetization measurements and work with data and learn how to code. And I I did not know how to do any of these things at first. So I'm still, learning new things all the time in our lab and learning new techniques and expanding my knowledge. And I think that's one of the best parts about getting to collaborate with Thalmon is like how much I can learn from him, all the things that he learns, and he imparts that knowledge on me. And yeah, I definitely think that's the way that I'm learning the most is from getting to work so closely with a graduate student like this.
Fantastic. Okay, now let us go forward in time. So this paper was all the research was done. The paper was written after months of hard work from both of you, and then the paper eventually went through reviews and got accepted. Either of you maybe tell us about this, the feeling of how when the paper got accepted, especially at editor's suggestion, how did it feel, and how was just this experience of going through submission and resubmission and replying to referees and getting your paper eventually accepted, and then making a figure for its publication or writing a summary, popular summary for its publication?
Yeah, and like if I have to be very honest, I was pretty confident that the paper would be accepted because that the data was very clean in the sense that so the effect this magnetoresistance it's very large, but it's already seen in few materials. It's already seen in it's actually in its parent material. So in fact, it was not a big surprise for us to see the effect. But what makes this material so special is that we can see many features of magnetoresistance which we see in very different materials. So it's like a perfect material to study where you see the aspects of many different CMR things just in one system. So that and we have done quite a lot of extensive deep study on this which I don't really see in generally happening. So I was like pretty confident that it will get accepted, but I was like very happy when I heard that it got editor's suggestion because that's something special. I think I went and had like an ice cream that day to celebrate.
So, as an undergrad, I understand that it's a pretty rare experience to be so involved in like such a large work, and that was a really special experience. And to receive such positive feedback on the paper from the reviewers and the editor was just it made me feel really excited and was really encouraging. And I definitely enjoyed that day and had fun. And it made me want to go to the lab more, like even more. Like the next day, I was like, okay, I'm ready to do the next thing. It definitely was very encouraging and super exciting.
Fantastic. Now, on that note, Mira, you also prepared an image. I mean, both of you actually prepared an image together for sort of advertising this work on Physical Review B website. Could you explain, tell our audience what is that image about and how did you make it and what was the process of making it?
Yeah, so we really wanted to show the two types of colossal magnetoresistance at one at high temperature, one at lower temperature, and really try to show how unique that was and kind of this overlapping of two different unique CMR. We really wanted to try to portray that in one image. So that was really cool experience because we had a lot of discussions on how we could show like these concepts visually, and I was really excited with how it turned out.
So maybe Sudaman, tell us first of all, did this how did you come to become a physicist? If I understand correctly, your undergraduate student was in engineering. Tell us about this shift from engineering to physics.
So so I was doing engineering. I specifically choose mechanical engineering because it contains a lot of physics. I was interested in physics from early stage actually, but the point is, so doing physics or doing basic science is not like a very big common route to follow in India, or more specifically in the place I come from. uh, it's called Telangana. So yeah, and there is like a joke that we have in India. It's people first do engineering and then they decide to see what they want to do in their life. So yeah. So in fact, I have so many of my friends from engineering who are not doing engineering. I don't think anyone from my close circle are doing or continuing being an engineer. They are actually in film and different stuff. So based on that, like once I was in the engineering program, at the end of it I was like, so because of this quantum hype, I got to know about quantum mechanics. Okay, and then I opened Griffiths. Actually, it's a very nice book, and then I started learning about it, and then I got more interested into the rigorous stuff of it. So that's how I know that okay, this working with quantum mechanics seems to be like a pretty fun thing, and then combining it with materials could be like an very can which can give like a very huge outcomes, and that's why I choose to go in this direction.
And you also had plenty of a lot of you always expressed interest in doing transport measurements, especially in the beginning. And you didn't really have a whole lot of interest in the beginning in details of materials aspects of the
Yeah.
research. First of all, tell us where did that interest in transport measurement come from? And then tell us about how did you become so interested in details of materials?
Yeah, and to be frank, I don't know where I got the interest from the transport measurements, but I generally like to see the electrons in motion and to see what they do. And then like going into the like once I was in PhD and was reading some papers and getting into some work, I got to know that this transport measurement is very important. Like very big discoveries are usually from transport in the sense like superconductivity. So if you see an high TC superconductor, you measure it using transport measurement. And yeah, so I sorry, quantum hall effect. I think that's one of the thing which I got very interested because of transport. So if you see, these two are the very big fields of condensed matter physics, strong correlations and topology, and both of them the like the poster child of those two data is transport data. So it has to be transport if you want to make like some very big discovery. So transport, the problem with transport, it has its limitations that we can't go deep into the thing, so we can't propose that this is the exact mechanism, but it's a beautiful tool for making the first discovery of things. So yeah, that's why I was interested in transport. And initially I wasn't interested in materials, and I can really understand why, because so if you see the crystals that we work with, they look very cute, but somehow I don't get interested in that. I like, for example, some people who are working in astronomy, their tools are like pretty big and pretty complex, and people working in lasers, optics, or some cold atoms. But in contrast to them, what we do in our lab, it's like a material which just looks like an stone. So people might initially think that what's fun in this field is not that fun. But once I started doing the measurements, I got to know, I mean, I always enjoyed getting the data from the sample. And then when I was learning things, I mean, I don't know when, I can't pinpoint it, but I understood that okay, all this data is actually coming from a material. So actually the action is going on there. So if you and if you just tune the structure a little, you can change so many things in the material. So that's when I understood the power of the the material science of it and the growth of it. Actually, Fazal told me so many times that is important, but to be frank, I never realized it from a verbal conversation, but it was really from the experiment. So I actually thank the PPMS in our lab to making me realize that the material is actually very important.
Excellent. Mira, how about you? So you told us that you had more of a chemistry interest in the beginning, but then over the course of this experiment, you became more interested in physics. So tell us about that transition and where do you think it will take you in the future?
Yeah, I really thought I was going to come to college and study maybe chemistry and become a doctor. And but I thought maybe I would still want to do research. Like the concept of research in general was always very interesting to me, but I hadn't exactly found, the perfect topic for me. And I think one of the best parts of joining Tafty Lab was that I was exposed to a lot of interdisciplinary concepts and ultimately did settle on physics. And I'm so happy about that and definitely feel very inspired by my graduate student and his work. And I've gotten to learn so many things that even I wouldn't have learned in my classes, just from getting to like see what other people in my lab are doing and participate in some of it myself. And I think one of the best parts of this project was working with our collaborators, and that process exposed me to so many different experiments that otherwise I don't think I would have gotten to learn about. And just getting to talk to all our collaborators who were so nice and always explained everything to me and let me engage in the conversation was just an invaluable experience.
Fantastic. So let's close maybe closing remarks. Maybe Mira, we start with you. You have done a full-blown undergraduate research experience in our group and at Boston College, and you still have work to do in our group before you graduate and go to the next stage of your education and research. But you're now a senior student and you've done this for some time. So what is your advice for other undergraduate students who are just fresh in their programs and thinking about finding a research group or doing some research?
Yeah, definitely, speak to the professor and find a professor that you really gel with. I think that was also one of the things that was immediately evident is that it was going to be a good fit for me, this group, and learn everything you can from whichever people that you can learn from. So if you can learn from other, undergrads that are more senior, or if you can learn from graduate students, just soak up as much information like a sponge as you can because that is just such an invaluable experience as an undergrad to get to participate in research.
Fantastic. And Sudaman, how about you? Closing remarks. You are this was your first experiment or experience, and you still have a long way to go to the end toward the end of your PhD. But at least for starting graduate students, do you have any friendly remarks that may help them in the beginnings of their research career?
I think I do have one. Actually, the thing with this project is, so in comparison to the projects that Fazal works with other grad students, I think the main difference is that there is not a big understanding in this project. So we actually don't know what we are doing, like when we come up with ideas. I think Fazal has some intuition, but definitely his intuition in the projects with he works with other grad students is like very like involved in the sense that they exactly know what they're doing. So if we read their papers, it's kind of very detailed in the science. So that was very difficult for me to get some motivation. But that's one particular thing I learned from Fazal is you have to be like an experimental spirit to do things. And I mean, he used to tell this even when he was teaching. But yeah, I think that's like the one biggest thing I learned in Tafty Lab till now. And I want to also continue that spirit and just have the attitude of just do it. And in fact, that's what I mean. The very new phenomenons that we discovered, which we are not talking now, were basically made because of the experimental spirit. It's impossible because these are very new that people have no theory on it. So it's impossible to get an idea and then do the experiment. So yeah, I think one suggestion is just be interested in experiments and do it. Like you don't need to have like an idea of things.
Yeah, well said. Indeed, it's really this exploratory spirit in science. It's really the most important aspect of discovering something new. You really want to be an explorer, and you shouldn't worry too much about understanding every detail about everything. Sometimes you just should let the data to guide you and teach you and reveal a new phenomenon to you. Whereas if you do something where you are 100% sure about it, the reality is that you probably won't learn anything new. So, yeah, well said, Sudaman. Very nice note to end. This is really, I think, what makes graduate school such a unique experience. You decide to somewhat be different and take this route of this pathway of being an explorer, discovering new things. All those things are, I think, it really satisfies a deep sense of curiosity in in human spirit. So, on that note, I would like to appreciate both of you. Thank you for deciding to going on this route. And I have to say that as your advisor, I also learned a lot of things from both of you. This has been such a wonderful exploratory research, and we're still learning new things, as both of you know. And we will definitely have another podcast on related materials. Thanks everyone for listening to our podcast.